Hey everyone, AMR back again with another LeetCode problem solving day. So I'm going to go ahead and show you this solution before we go ahead and get into another problem. This is a really cool problem that I ended up solving last night. So basically what it says is check if every row and column contains all numbers. If you're very familiar with how the game Sudoku is played, you know that all of the numbers from left to right in a row have to be between 1 and 9. And then they have no repeats. And then same thing goes for the columns. So for every column that goes straight down, same thing applies, 1 through 9, no repeats. And then for every sub box, in this case, this is just a 3 by 3 or an n by n, where n is literally going to be, 3, 6, 9, whatever. And these sub boxes are basically going to make up a bigger Sudoku problem. This problem was given to me by suggestion for solving the other Sudoku problem that I had already solved. And basically what I'm doing here is I have a completed Sudoku puzzle here, very small, 3 by 3 in this case. And the thing is going to be passed in as a matrix. So it's going to be a nested list where you have to check and see if this is a valid matrix. So in that case, has to be numbers 1 through n, and there can be so if this satisfies and this satisfies, and then so on and so forth until you get all the way through, then you have a valid matrix. Only then do you know that you have a valid matrix. So let's go ahead and talk a little bit about what I did here. So first off, I went ahead and thought about how I'm going to be iterating over the actual matrix itself. So I did a for I in range len of matrix. I don't really care about what the value is at this point in the problem, because all I care about is tracking which type of row that I'm currently in. And so what I do here is I call my helper methods. So I have a helper method called check row. This actually checks the row of what I'm actually looking at for the matrix. So in this case, if I is 0, it's going to look at that first row and then validate in some form or another. We'll get into that in a second. And then as long as the other helper method, the check column, also passes, then we should be good to go. And so for the way that I'm doing the helper methods here, so you have a row. What I did is I did a set of the row and then I sorted it. So that way I have, ideally the row would look just like how this row 0 is. 0, it would be like 1, 2, and 3, right? And then all I do here is I say if the sorted row 0 is not equal to 1, we have some constraints that we have to go over here. So n is going to be equal to 1 or 100, and so on and so forth goes down the line for the columns as well. And then I think that there's another one right here. Yep. So all integers are going to go from 1 to n inclusively. So as long as the sorted row of position 0 is not equal to 1, or the last element in the row is not equal to the length of the row. So in this case, if you had a row with 3 elements in it, you're checking to make sure that this one is 0 and then this one is 3, or the length of the sorted set. So really important here, because in a set you have no repeats. So if you had 1, 2, and 2, the thing would be 1, 2, and that would not equal the length of the original row passed in. So you don't actually have to do a ton of saying, okay, I'm checking each individual value and making sure that it's greater than the value before it. You don't have to do that in this case. I just go ahead and return true. I do a very similar approach for the column. As you can see, it's damn near the exact same code, just making it more specific to a column for readability purposes. And then down here in the matrix itself, I'm passing in the individual row that we're looking at for the indice in the matrix. So we look at that first row and then we say, okay, so given that we know that we're on this first row right here, I'm going to have that be the indication of what column I want to look at. And then I'm going to say for j in range len of this. So we know that it's a perfect square. And so what this is going to be doing is it's going to start off at 0, 1, and so So what this is going to do is it's going to go 0, 1, 2, and then you also know that this is going to be a static value because it is not changing within this additional for loop that's going to be happening. So when I is 0, so you have 0 right here, you're only looking at that first positional element, and then you're going to be looping down the entire matrix. So you're going to say 0, 0, 0, 0, 0, 0, 0, 0, 0, as so on and so forth. And then only in the case where all of that passes do we return true. If at any point in time when we're iterating over each row and column that we get one of these values that is not returning a true value, we just go ahead and return false because we know that it is an invalid matrix. So one really cool thing that I want to talk about here is that my first submission I did pretty poorly on. It had, as you can see, 1200 milliseconds to operate around the same memory. So I'm not really too concerned about the memory of this. You know, it's a pretty big problem, and I think that there isn't more optimal solution. I'm not going to sit here and say that I have the best, obviously, but when I went back and I created these helper methods, and then I really honed into what the constraints are of the problem. I was able to just check that element 0, element 1, making sure that the set and the original list are the same length. If all that checks out, then we know that we have a perfect list given the constraints of the problem. And so once I did that, I sped up exponentially in this problem. So I went from 1200 down to 800, which is a vast improvement. 68.65% of submissions are slower than my problem or my solution in that case. But that's enough about this problem. I just want to go ahead and show that off a little bit before we go ahead and jump into another one. As always, if you like the content, feel free to like, comment, subscribe. Helps me out a ton. And let's go ahead and jump into a new problem. All right, so here we go for our next problem. It is integer to Romans. So this is a very, very common problem, especially when you're starting out. There's an easier one where it's Roman to integers. It's basically the same problem, it's just inverse. So given a integer, you are going to subtract it down until you get its Roman equivalent. So a couple of caveats here that you have to think about is each one of these symbols actually has a meaning, okay? All that makes sense, but the bigger part here that we have to consider is that there are things called subtractables, or that's at least what I'm going to refer to them as, where if you have a IV and an IX, that changes 5 to 4 and 10 to 9 respectively. Same thing for XL, XC, CD, and CM. So I'm going to go ahead and convert these over into, I'm going to convert these into a list, basically, or actually not a list, but a dictionary. So I'm going to say subtractables equals this, okay? And then I am going to say 900, and that is going to be equivalent to CM. You are going to have 500 equal to CD. Excuse my typing, it's getting a little hairy here. You have 90, which is going to be equal to XC. You're going to have 40 with the XL. You're going to have 9. It's equal to IX. Then you're going to have 4 equal to IV. Okay. Additions. I would say like additionables, but that doesn't make any sense. You know, I don't think really mine makes sense either. But the rest of them, self-explanatory, make an I. You have 5 equal to V. You have 10 equal to X. This shit is like really pissing me off here. L equal to 50. You have C. I keep wanting to do it the opposite way. I apologize for that. C. You have 500 equal to D. And then you have 1000 equal to M. Okay, so here we have a number. We're just going to say while num is greater than or greater than 0, we're going to say, yeah, so we're going to have a string. We're going to say output equals that. Okay. So we are going to sorted subtractables equals sorted. They're going to say subtractables dot items sub lam the x sub 0. You want reverse equals true. Sorted additions equals sorted additions dot items lambda x sub 0 reverse equals true. Boom. Okay. So a couple of things to think about here. You have your, how would you write this? Looking over here at our examples, 58 is written as LV. So 55, 8. Okay. So it takes the largest thing first. M. Okay. So, okay. While num. Okay. Actually, I don't think we need to do this part. We know what like the limitations are. So if num divisible by 1,000, let's look at this here. Just give me anything. I don't give a shit. Python console. Okay, A is equal to 1994. A divisible by 1,000 equals 994. Okay, what happens if I do 994 divisible by that? Maybe I just need to do A like this was 1. Okay, 994 equals 0. All right. Okay, so we have thousands. It's going to be equal to, yep. You have thousands is going to be equal to num divisible by 1,000. That makes sense. Hundreds. Hold up. If thousands greater than 0, num equals minus equals thousands times 1,000. I think now I do 900. 900 equals num divisible by 900. If 900 greater than 0, num minus equal 900 times 900. So on and so forth. Just keep doing this. So then you go here, go 500. I can definitely optimize this. I'm just doing this for the time being to get that solution going. 500, 500, 400. Probably end up fast forwarding this. Okay, so I've done this enough now to where I think I can do this. Def subtract unpack and subtract. Okay, give a num and a divisible. We're just gonna say val is going to be equal to num divisible by divisible if val is greater than 0, num minus equal val times divisible, return val num. Okay, thousands equals unpack and subtract num 1000, 900 unpack and subtract num 900 get out of the while loop now. Don't need that anymore. Over here, go like this. Okay, so we have 500, 500, 400, 100, hundreds, 400s, 500s, 900s. You got your 90s, have your 50s, have your 40s, have your 10s, I want to say. So 40, 50s, 40s, 10s, 10s, 5s, and then the last one will be 1s. Okay, it's gonna go 500, 400, 100, 90, 50, 40, 10, 5, 1. Do I really need to do 4s? I do need to do 4s as well. 4s and 9s. Okay, so here we go. All right, so your output is going to be equal to an F string. Okay, it is going to be thousands. So it'll be additions, sub 1000 times thousands it will then be addition or subtractables sub 900 times 900s Ugh. What a beefy problem. Seems like a lot, but I guarantee you it's damn. All right. 58 and 1994. Let's just see if these test cases pass. As you can see, we have an accepted output here. All of that looks fantastic. Let's hit the submit button and see where we're at. So our our memory allocation is pretty dog shit. It's 7.07%. It is relatively quick though. So let's go ahead and see if there's any ways of optimizing this. I would think that instead of storing these in the additions, we could literally just go like, where's the 1000? 1000 would be M. You could do this as CM or is it DM? CM, okay. M, CM, D, DM, okay. D, DM, C, is it XC? I think it's XC. That makes sense. 50 would just be L. 40 would be XL. 10s would just be X. 9 would be IX. 5s would just be the V. 4 would be IV. And then you would have 1s just be the I. And then we can go up to here and we can just go like so. And we could probably just get rid of the output because it's unwanted code. Bada bing, bada boom. This should work. Okay. Let's see what we did wrong. 4s, 5s. Oh, it's because I'm dumb. There we go. Now it should work. Let's see where we're at. Wrong answer. Cool. Output. DM. I think I screwed up 400. What was 400 supposed to be? 400 is CM, not DM. Okay, that's why you run these tests. Got the wrong answer again. Oh, it's expected to be CD, my fault. Okay. So still not super efficient on the space. Okay. I think I'm just trying to think about how we can get this memory down. I think that by unpacking them all like this, it's probably not the most efficient way of doing it. So I'm going to guess that we could just have output equals empty string like such. You pass in the output value. Num divisible, and then a char. Okay. Instead of returning that, you could return num, which that makes sense. Instead of returning a value here, you could return output. And then you would go output plus equals. Let's look down here. Output plus equals char times val just times val. Yeah. That makes sense. Hopefully. Okay. And then you could just say while num is greater than 0. And then instead of all this, you could just say output this. You could probably you don't necessarily need it to be a while loop, but for our purposes, we'll go ahead and keep it as such. Num divisible output. And in this case, it'd be M. Is that right? MCM. Just like this. Like that. Don't even need the while loop anymore. Could literally go like this. Say 900, 500, 400, 100, 90, 50, 40, 10, 9, 5, 4, 1. Okay. M, CM, D, CD, C, X, C, 50 would be L, XL, X, IX, V, IV, I. Output is all that. Just return output. Wrong answer. Gotta remember the F string, buddy. Now I'm predicting that this one's gonna be pretty fast and pretty space efficient. It's actually dog shit and dog shit. So I don't know what else to tell you. I'm guessing that there's probably a way to, I mean, you could probably just directly, I don't know, man. I'm actually happy with the solution. I don't care. It was fast at one point and then I made it slower and slower. Let's go ahead and run it again, just see what happens. 93 milliseconds, and now it's, you know, more efficient all of a sudden. I think it really just depends on when you run it. I'm guaranteeing that if I run it again, it's just going to be, you know, about the same. Look at this, like now it's 92.72%. It really just depends on how fast the thing can actually work. I was super happy with the overall solution. It is, I mean, it's super efficient in terms of memory allocation, in my personal opinion. I don't really know how someone else could do it better than this. But anyway, that's going to do it for today's video. As always, if you like today's content, feel free to like, comment, subscribe, helps me out a ton, and I'll catch you in the next one. See you.